Hello and welcome to another LeetCode video. Today we're going to be working on missing element in a sorted array. And in this problem, you're given an integer array nums which is sorted in ascending order and all of its elements are unique. And also an integer k. Return the kth missing number starting from the leftmost of the array. So in these examples, we have example 1 where we have 4, 7, 9, 10. And so they draw out the missing numbers here. So the missing numbers have to start from the start. So like 1, 2, and 3 aren't missing. It's from the left. So what's missing? So 5, 6, and so on. And then 5 is the first missing number. So we're going to return 5. Okay, the second example, we have 4, 7, 9, 10. And so what's missing here? So 5, 6, then the next one is 8. So 8 is the third one. So we will be returning 8. And then finally we have 1, 2, 4. And the number missing here is 3. So that's one number that's missing. And then afterwards, the numbers that are missing are numbers that are bigger than the last element in that array. So it'll be like 3, 5, 6, and so on, right? 7. And so the third missing number is 6. Okay. So where would we start with this problem essentially? How would we even begin? So what you could do is you could have a brute force solution, right? Where like, let's say you have this 4, 7, 9, 10. So if you did have this 4, 7, 9, 10. Okay. So you can just go through this array and then you can just make an array of numbers that are missing, right? So you can have like 5, 6, 8, and then after you make an array of numbers that are missing, you can just calculate like, okay, is k in this array, like is k 3 or less? And if it's not, then you can just calculate like what's the next number logically, right? So you know like the missing number would be like 11, and then from there you could figure out like, you could write maybe like 11 as the next missing number, and then you could figure out, you know, what's the difference between that and k. So if like 11 is the fourth missing number and you need something like 5,000, right, it's probably going to be something like 11 plus 5,000 minus 4 roughly, or something like that. And what's going to be the time and space complexity for this kind of solution? So it's actually going to be O of n time and O of n space, right? And we need to see if we can do better. So how would we do better? First of all, can we, getting a number, know how many missing numbers there are up to that point? Like, let's say we have this 4, 7, 9, 10, right? Like, let's say we just get this 9, and we know this 9 is at index 2. How many numbers are missing? So we can't actually figure that out, and that's going to be the key. That's going to be one of the keys to this problem is we know that if 9 is at index 2, so 9 index 2, right? And then we also know the first element, so 4 is at index 0, right? Then we can figure out what should be at index 2 if no numbers are missing. So if no numbers are missing, it should go 4, 5, 6, right? So we know that 4 should be at index, or sorry, 6 should be at index 2, right? Because we know the starting number and we know what index we're at. So we could just do 4 plus 2 and we could say, okay, 6 needs to be here. We have 9. So how many numbers are missing? Well, it's pretty straightforward. It's just 9 minus 6, so that's 3 numbers. So we can calculate for every single number how many numbers are missing up until like, or for where we're at. So now that we know how to do that, we can do that for any number, right? So same thing for like a 1, 2, 4, we can do the same thing. We can say like, okay, let's say we have this 4. This is at index 2, starts at index, the first number is 1. So we could do like 1 plus 2 should be 3. We have 4, so one number is missing. Okay, so now that we know that like how many numbers are missing, what else do we need to calculate for this problem? Like what do we actually need? So what we actually need is we need, what I thought at least, we need a left bound and a right bound for the numbers that are missing. So like we need a number that's a left bound for the numbers that are missing. So like let's say for this first example, let's say we would need the 4 would be the left bound, right? We actually would need the index. So we'd need like index 0 because, so let's actually draw this out. So for this 4, 7, 9, 10, and we are asked for k equals 1, I thought originally that you need the left bound and the right bound for the numbers that are missing. So here, this would be like index 0, and this would be index 1. And these are the two numbers that you need, because here there are 0 numbers missing, and here there are 2 numbers missing. So then k is somewhere in between those. And I thought you like, oh, you need a left bound and a right bound, and then you can actually calculate like what's the missing number. It turns out you actually need the rightmost left bound. After like I had the left bound and the right bound, and I actually got those. And then it turns out you don't actually need the right bound. You just need the left bound. And then as long as the number to the right of that is k or greater, this will work. So essentially what you do is you get your left bound, and then you say, okay, at this, there are 0 numbers missing. So what am I looking for? So k is 1. So if there are 0 numbers missing, and I have 4, and I need the first missing number, then you know that at the next number, k is 1 or more, right? We're going to calculate the left bound and the right bound. So if we know that k is 1 or more, that means this number can't be 5, right? If you think about it, like if this number was 5, then k would still be 0. Or like there would be 0 missing numbers. And we know because we calculated a left bound and a right bound right next to each other, right? The left bound, let's actually write this down. So the left bound is going to be the index of, let's make this a little bit bigger. So it's going to be the index of the number where there are less than k missing numbers. And then the right bound, so the right bound should be index of the number right after it where there are k or more missing numbers. But yeah, it turns out you don't actually need this right bound, and so you can also have the case, right, where like if you have numbers like 1, 2, 3, 4, and k is like 100, then you won't even have a right bound, right? You'll have a left bound that's over here, and then the right bound will be out of bounds. So you don't even need this, it turns out, but let me show you why once again. So here there are 0 missing numbers, and here there are 2 missing numbers, and for k equals 1, we've like fit this criteria. So this could be a left bound, this could be a right bound, right? Because for the left one, there are less than k missing numbers, there are 0, and for the right bound, there are k or more, there are 1, and we're looking for 1. Or sorry, there are actually 2 missing numbers here, and we're looking for 1. Okay, so now that you know that like 5, this can't be 5, because then there will be 0 missing numbers again, right? And so if k is 1, that means we can just say, okay, let's just take our left bound, and however many more numbers we need, like let's say if there's 0 missing numbers, and there's 1 that we need, we would just do 4 plus 1, and that would give us 5. And the same thing if k equals 2, we know if this was our right bound once again, which it is, we know that this can't be 6, right? Because if this is 6, then there's only 1 missing number, right? There's only 5. So it can't be 6, and so our output would be this left bound plus the number of more missing numbers that we need. So we have 0, we need 2, so we'd add 2, and then our result would be 6. And then we can even do this for another example. So we can do this, let's say k was 3, just to keep going with this like kind of stuff. So let's say k was 3. Let's actually delete these. K is 3. Okay, so now what's going to be our left and right bound for this case? So for the left bound, we need something less than 3, and then the number after it. So you can kind of already see also, for the left bound and the right bound, you don't actually need to save. Like, even if you needed this right bound needs to come right after the left bound. It needs to be like left and then right. Then it needs to be the index after. So you wouldn't even need to save this anyway, but regardless. So let's see what's missing. Like, so there's a 5 and a 6 missing. So for here, k equals 2, right? So for this number, k equals 2. So this is actually going to be our left bound. So this is going to be our left bound, and this is going to be our right bound, because here there are 3 missing numbers, right? There's 5, 6, and 8. So now let's do this again and realize that this cannot be, if there's 3 missing numbers, so there's 2 missing numbers here, and there's 3 missing numbers here. this number can't be 8. Because if this number was 8, then there would be only 2 missing numbers. So it would be the same thing. It would be, if you think about it, it would be the exact same thing. You would take your left, whatever that number is, 7, and then you would say, how many more numbers do I need to get to k? Well, I have 2 missing, I need 3. So I need 1 more. So you're going to add 1, and you're going to get 8. And so that's your solution to getting that. So let's write that down, maybe in another color, or let's just write some steps, and then we need to also figure out how do we actually do that quickly. So we actually need the number, the rightmost number, or really the index, right? The index of the rightmost number where the number of missing, I'm definitely saying number a lot, but numbers is less than k. And we're always going to have that because it either has to be one of these, like there has to be either a left bound and a right bound in here, or the left bound is going to be this last number here, and then the right bound just out of bounds, right? For the example of like, if we have something like 1, 2, 3, and k is 100, then obviously the left bound would be here, and then the right bound would be, out of bounds. So we're still going to have that, but we don't need the right bound. Okay, so we need the index of the rightmost number where the number of missing numbers is less than k. And finally, to calculate missing numbers for an index, how do we do that again? So it's going to be the value of that index, or like so for an index is going to be the value at that index minus what the value that should be in that index, which is just nums0 plus index, right? So for this 7, let's say, this needs to be a 5. And so to calculate how many missing numbers there are, it's going to be 7 minus 4 plus that index. So that's going to be 2 missing numbers. So we can calculate missing numbers in big O of 1 time. And we need the rightmost number where the missing numbers is less than k. So now that we know that this is sorted, we can also do a binary search here, right? Like pretty straightforward. Like let's say we have this again, right? So we have this 4, 7, 9, 10. And we are looking for k equals, let's say, 3 or 2 or whatever we want, right? Like, let's say it's 3. Let's just say k equals 3. Okay. So what we need is we need the number that's less than k, but it's the rightmost number. So let's just show you what that's going to look like really quick. So the left is going to start over here. The right is going to start over here. And then the first pivot value is going to be the 7. And we're going to say, okay, we have a pivot value. So for the 7, how many missing numbers are there? Well, there's actually 2. Okay. There's 2, and once again, we're gonna record like this. I'm gonna do this as I normally do it. I'm gonna record the rightmost valid location, and so let's have this. Let's delete some stuff. Just have some space. Okay, let's delete this. Let's delete this, and now we have some space. So I'm gonna have like a result, which is gonna be this thing that we're looking for here, the rightmost number with the missing numbers missing. Let's call that result, and let's set it equal to left because we're trying to maximize it. So let's just set it equal to 0 or something. So the first pivot is going to be 7, and how many numbers are there missing? There's actually 2 numbers missing. So this is a valid. This could be the index we're looking for. So we're going to actually update our result to be 1, and now remember we're trying to maximize our result. So if this is valid, now we're going to delete this, and we're going to actually move our left over here, right? Because we're trying to maximize it. So this whole part of the binary search is gone. Now we're going to have the left and the right. The pivot is going to be over here. And now we're going to say how many numbers are missing here. So there's a 5, 6, 8. So now there's 3 numbers missing, right? So there's 3 numbers missing. So this can't be our result because we need a number that's less, right? So this can't be. And so we're not going to update our value, and our right is actually going to go over here. And now we have a broken condition for a binary search. So the number we needed was this number over here, and that's the index. So and then we're going to say, okay, for this index 7, how many numbers are missing and how many numbers do we need? Well, or sorry, for this index 1, we have 2 numbers missing, right, from our calculation of 7 minus 5, and then we need 1 more because we need 3, so we're going to do 7 plus 1, 8 is going to be our result. And so that's kind of how you do this problem. Once you understand that you can calculate the numbers missing in O of 1 time, and actually what you're looking for, you don't need a left and a right bound, you just need a left bound. This will always work. Okay, and so now we have enough to code it. And we can actually show that for this example here really quick, by the way. So let's just say, let's look at this example 3, and let's just show you that it'll work if the number is out of bounds as well. So for this, 1, 2, 4. Okay, let me just draw that. It's a little laggy for some reason. Okay. So here, our index is going to end up over here, our like leftmost or our rightmost index that's less than k. So here there's 1 number missing, and we need 3. So what we're going to do is we're going to say we have 1 number missing, we need 3, so we're going to do 4 plus 2. And that's going to be 6, and that's going to be our answer as well, as you can see here. Okay, so now we have enough to code. So let's make a left and a right. Equals 0. We're going to make it from the whole thing. Now we're going to make our result, and this is going to be our, index that we're trying to maximize. It's going to be the rightmost value that's less than k. We're going to start it at the left. We're going to say, well, left is less than or equal to right. We're going to make a pivot. That's right. Mod 2. And then what we need to do is we need to actually calculate the number of numbers that are missing, right? So how do we actually do that? So we can just call that like missing numbers or something. Equals, what's that going to be? So it's actually going to be nums pivot minus, and then remember it's nums 0 plus pivot. That's going to be the number that should be there. For example, if pivot was 2, then we would say, okay, num 0 plus pivot, this should be 6. So we'll do 9 minus 6, so there's 3 numbers missing. So there's this many numbers missing, and now finally, we can actually write this directly if we wanted to. So we can actually say if, without even using this variable, we can say if this is greater than or equal to k, that means that we have too many missing numbers, so we don't want to update our result to that. We actually want to go to the left, right? Equals pivot minus 1. Otherwise, our number could be a valid, rightmost valid number, and then that means we need to actually update our result. So we could say update our result equals max result pivot. And then we're trying to maximize it. So if we have a valid value and we're trying to maximize it, we're going to go right now. Equals pivot plus 1. Okay, so now that we have the rightmost number that's less than or equal to k, what's our actual result? So what do we need to return? Well, it's going to be the same missing numbers calculation, right? So it's going to be like missing numbers equals like how many more numbers do we need essentially, right? So it's going to be like what do we need to add to it essentially, right? So it's going to be like what number do we have? It's going to be nums pivot. Right, so we can figure that out. So for nums pivot, how many numbers are missing? So it's actually not nums pivot, sorry, it's going to be nums result. It's going to be the same thing, minus nums 0 minus the index of the result. So that's going to be that. That's how many numbers are missing. And then we finally need to say, okay, let's return nums result plus however many more numbers we need. So like, for this example, if we have 2 numbers missing, but we need 3, this would be k minus missing numbers, right? Something like that, I believe. So let's just give that a whirl. Okay, so we have something wrong here. So let's just double check this, and let's just double check everything, actually. They do a lot of simplification, but that's okay. Okay. So missing numbers is this. This would be plus, right? Because like for the same example, if this was index 1, then we would say, okay, let's take the first number plus 1. We have 7 minus 5, and we're missing 2. Okay, so let's just double check that that works. Okay, so that does work. Now we could actually simplify a little bit. So you could see that we have this missing numbers. So we can actually throw that into here. And now we could do a little bit of simplifying, right? So now this is what we have. So we have nums result plus k minus this stuff. So we could actually simplify that, I believe. And so this ends up being, let me actually go back. So this part is negative, and then k is minusing this thing, essentially. So this result will cancel out with this result. Like if I actually draw it like this, it'll be a little bit more clear. So what we actually need is we need a negative, right? So minus negative, and then it's going to be like this whole thing, essentially. So if you throw that in there, this is actually going to be a, or actually 1 second. I think I did it a little wrong. Yeah. So it's not actually going to be minus negative. This part will be minus negative, but this result will be minus that number. So it's actually going to be something like this. It's going to be minus, I can draw it in here and that'll make it pretty clear. Okay, so it's actually going to be like this. And now you could see that it's num's result minus num's result, so these actually cancel. So we can get rid of these. And now it's k minus negative this whole thing. So that means it's actually k plus all these items here. So it's actually this once you cancel this stuff out. And let's try that as well. Guess that does work. So essentially, once you write out the missing numbers, you see a bunch of stuff cancels. And you can see it's a very efficient solution because we used logarithmic time. And so let's go over the time and space complexity here. But yeah, I think the tricky part about this problem is just understanding that you can calculate how many numbers are missing in big O of 1 time, and then what you actually need. Once you get the rightmost value that's less than k, that means that the kth available number is always going to be available. It's never going to be in the array. Otherwise, the number to the right of it would never be would never be k or less. It would be less than k as well. Okay. So for the time, it's logarithmic, right? Because we have a binary search. And for the space, it is O of 1 time because we don't have anything, I believe. Yeah, we don't have any like arrays or anything. We just have a left and a right and a result. All right, so that's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.